Hello, my name is Eric Blair, and this is the second part of my talk on quantum dot cellular automata. In the first part of my talk, I gave you an overview of QCA, in particular a molecular implementation. I showed you basic QCA devices. I showed you how they can be put together and how they can be clocked using an external electric field. So we bury these conducting wires to generate an electric field which activates and deactivates molecules synchronously. And I showed you how we can put devices together in a hierarchical manner to get extremely complex circuits. In this part of the talk, I focus on research in the QCA that I've done personally. So we're looking at this set of items here. In the last part of the talk, we introduced how we can use clocking wires to control QCA via an external electric field. And one of the questions that comes up is whether we defeat the purpose of QCA, that is to say, whether we introduce more power dissipation by clocking using these clocking wires, because now we have conductors, we have current that has to flow through these wires, and do we shoot ourselves in the foot? And the answer, as it turns out, is no. I did some simple calculations using clocking wires of reasonable dimensions, and the simulations that I ran revealed that power dissipation in the clocking wires is actually quite manageable, even at frequencies like 100 gigahertz. It's well below the limit of manageable power dissipation. And that leads us to the conclusion that power dissipation in the molecules themselves is where we need to turn our attention and our focus. It's not the wires that will give us a problem. In molecular QCA, and clocked QCA in particular, one method we have for minimizing power dissipation is called erasure with a copy. The idea is that if we can erase a copy of a bit in the presence of a copy of itself, then we need not dissipate the bit energy of the erased copy to the environment. And so what happens, the circuit here that demonstrates this is a fan-out, fan-in circuit where one bit comes in from the left, it branches out into 2-bit packets here at column A, and then the 2-bit packets are jammed back together into one, with 1-bit packet leaving. And in the right, we have energy input from the clock, so we see an energy expenditure to create the second bit packet. But when that second bit packet is deleted or erased with a copy, the energy from that bit packet is returned to the clock rather than dissipated as heat. And so that is a savings in power dissipation. And we will talk more about this later, but that really is a demonstration of Landauer's principle. Another question that arises is that of quantum decoherence. Quantum decoherence is driven by the interaction of a quantum system with its environment, and in quantum computing, quantum decoherence is fatal. Now, QCA is not quantum computing. In fact, it is a form of classical computing because the bits are classical, and it's also been called quasi-quantum because it requires quantum mechanics to for the function of QCA cells. But the question arises, well, what does decoherence do to QCA cells? And as it turns out, we've found that decoherence stabilizes bits in molecular QCA. So here is the polarization of a 2-dot cell, and this cell is isolated, and its evolution, as you can see, is actually unstable. The cell just flips back and forth between the 1 bit and the 0 bit. The time scale here is given in terms of this tau, which is the Rabi oscillation period of this system. But now consider what happens if we give that isolated molecule an environment. So it's no longer isolated. Here is that molecule now with 8 neighbors, and the polarization of the cell is now stabilized in time. There are no bit flips in this picture. And that is a surprising fact, given that the molecules themselves, the neighboring molecules, are all neutrally charged. And they still have an impact on stabilizing the target molecule. And here's an overview of some work that was published just this summer. The focus here is electron transfer in molecular QCA. Both electron transfer and power dissipation are important in molecular QCA. And so it's essential to model these, and models of these allow us to ask the question, well, how fast is a molecule and how much power does it dissipate? So the idea is this. Here is a 2-dot molecule. These iron centers each are surrounded by these carbon rings, cyclopentane, I believe. And as the electron hops back and forth between the 2 dots, the dots provided by the molecules, or the atoms around these dots, that is the 2 iron centers, deflect. Their positions deflect, and we get what we call vibronic motion in the molecule. And this is how the molecule will actually dissipate power and energy to the environment. Again, there's no resistive heating here, but this turns out to play an important part in the power dissipation in a QCA molecule. So the physical system that we're modeling here includes an electron. So where is it located on the molecule? And it includes vibronic motion, the vibron here. There's a link between the two. And then the environment is linked only to the vibron, so that power dissipation to and from the environment is only to the vibronic motion of the molecule. So let's look at parts of this model, starting with the electronic system. So here are the 2 states of the electronic system. One state has the electron on the left dot, and the other state has the electron on the right dot. It's the sign of molecular polarization that encodes binary information. This is the Hamiltonian for that molecule, and this captures the energetics of the molecule, including transitions between the 2 dots and a bias between the 2 dots. This gamma is the hopping energy, which describes those transitions, and then this delta is the bias. We can use that Hamiltonian to calculate the cell-cell response function. So there's going to be a driver molecule, and its polarization defines the delta for the Hamiltonian. And we consider various values of gamma, and we find the ground state for the target cell, and here we get this curve. Now it's inverted from the first curve that I showed you in the last presentation because we're dealing with half cells here, and these half cells, these are 2-dot cells, they tend to align oppositely, or they anti-align, whereas the 4-dot cells align exactly. The next part of the model is a vibron, which we model using a quantum harmonic oscillator. This is the vibrational movement of the molecule. And the Hamiltonian for that is written like this. There's a kinetic energy, a potential energy, and we can rewrite it in terms of the annihilation and creation operators. We can use the time-dependent Schrödinger equation to model the dynamics of this system, noting that this equation gives us only closed system dynamics, because the Hamiltonian conserves energy, so energy can neither enter or leave into the system. And as you recall, the whole object here is to get power transfer to the environment from the vibron, so we'll have to build in energy transfer some other way, and we'll show you that in a moment here. But for now, we'll consider the stationary states of the quantum harmonic oscillator. They're shown here on the right. There's a parabolic potential that defines the oscillator, and then the probability distribution is shown for each of the various evenly spaced eigenstates of the oscillator, and the eigenstates have energy spacing h bar omega. And the annihilation and creation operators transition the system between adjacent states. So the annihilation operator takes an eigenstate and lowers it to the next lower level, whereas the creation operator excites a state to the next higher level. And this video demonstrates the quantum harmonic oscillator's time evolution. In the upper right, here's a plot that shows the parabolic potential, the discretized energy levels in purple lines, and in green it's the expectation value of energy for the system, and the probability distribution for the vibron in position or in space is given here. Or you can also think of this Q as reaction coordinate. And as I play this video, you're going to see that the energy spectrum here on the left does not change because the system is a closed system, that is, it can't gain or lose energy. But that's not going to stop the probability distribution from changing as a function of time. In fact, you can already see it in this bottom picture where the region of high probability is oscillating. And you can see the conservation of energy here in the bottom part of that picture. So let me play that for you. Oops, I have to go back. So the system's energy is constant because we're using the Schrödinger equation. Now we want to build in power transfer to the environment, so we're going to allow the environment to damp the vibrational motion of the molecule. So to do that, we have to go from the Schrödinger equation to something else, the quantum Liouville equation, and in order to do that, we need to go from wave function formalism to density operator formalism. And in this picture, the quantum Liouville equation here is equivalent to the Schrödinger equation. So we have to add more to this equation. And the extended equation we're going to use is the Lindblad equation, which models the system as an open system. It includes, as you can see, the quantum Liouville equation, but then there's this Lindbladian term which models the effects of the environment. So a specific model of the environment requires a specific choice of Lindblad operators, and as it turns out, the L1 here relaxes the system. Notice it's proportional to the annihilation operator. L2 introduces decoherence, and thermalization can be achieved using L1 and L3 in concert, where Kb is Boltzmann's constant and T is temperature. And so this drives the system to a Boltzmann distribution at a certain temperature. Notice that L3 is proportional to the raising operator or the creation operator. And using the thermalization, we can now show what happens to our system. It's no longer a closed system. As you can see, the vibron is going to lose energy, so its power level is going to drop. And you can see that. The energy spectrum is changing, and it's approaching a Gaussian distribution, or not a Gaussian, I'm sorry, but a Boltzmann distribution. And you can see here that energy has decreased in time. So that's how we model power transfer from the vibron to the environment. And now we need to link the electron and the vibron together. So to do that, we use a reorganization energy, which defines a coupling term, and that coupling term then defines a coupling Hamiltonian. And so the total Hamiltonian is the electron's Hamiltonian plus the vibron's Hamiltonian and the coupling term, which is the glue that puts these two together, the linker between the two. And we put this Hamiltonian into the Lindblad equation once again. And we get results like this. Here's a calculation in which I show or determine electron transfer time for the system. So what we do is we take a driver and we set its state like this, and we allow the target molecule to relax. And of course it wants to anti-align. But at some time which we define 0, we abruptly switch the state of the driver, and we allow the target electron, or the target molecule's electron, to tunnel, and we calculate the time that it takes, or we record the time that it takes the molecule or the electron to go from the left dot to the right dot. And so we define that time as the time for electron transfer, and then we get an electron transfer rate, k, by taking the inverse of the electron transfer time. And of course, this has units of inverse seconds. So what we're looking at here is polarization. This is the electronic response to the switch in the driver. And then on the bottom we have the probability distribution in time and reaction coordinate for the vibron. And you can see they're distinct but related. And so using various calculations like this, I can model things like what's the response of the molecule to different temperatures. And what you can see here is that for a wide range in temperatures, the electron transfer rate is relatively high, of the order of 10 to the 12th electron transfers per second. And so that speaks of terahertz frequency operation. So very fast device switching. Here's another one in which I say, well, what if we vary the reorganization energy? And the reorganization energy, again, that determines the strength of the coupling between the electron and the vibron. And even still, we're getting some very high electron transfer rates, again of the order 10 to the 12th electron transfers per second. And here's another model in which I vary the environmental coupling. And again, so this is the environmental coupling between the vibron and the environment. And again, we're seeing very high electron transfer rates. Finally, here's a picture of power dissipation in molecular QCA. The idea here is based on Landauer's principle of minimal power dissipation. So Landauer used entropy to argue that the minimum energy of computation is kT log 2 for every irreversible bit destruction. That is, every time we erase a bit and we can't get back which bit we just erased, we must dissipate no less than kT log 2, where T is temperature, Kb is Boltzmann's constant. However, if a bit is erased reversibly, that is, it's done in the presence of a copy, by which we can determine what the original bit was, energy need not be dissipated. Now, in QCA, the devices are very small, and we can get very high device densities of the order of 10 to the 14th devices per square centimeter. Contrast that with device densities in modern-day transistors, which are between 1 billion and 10 billion devices per square centimeter. So with packing densities like that, we ask, well, what if each cell in a tight-packed QCA array dissipates an energy of just kT log 2 every clock cycle? Well, if that is the case, then that puts us on this red line here on this chart where we have power dissipation per unit area on the y-axis as a function of clock frequency. And on this red line, we're considering maximum packing and dissipation of 1 kT log 2 every clock cycle. Now, we can afford more dissipation if we reduce the packing factor, but in any case, this red line is well above the limit of manageable dissipation. We would rather be on the purple line, and we can achieve that by dissipating 1/100th of a kT log 2 every clock cycle at maximum packing. And this really just shows us that at device densities afforded by QCA, the system must be operated with a very high degree of adiabaticity. That is to say, we must use reversible erasures, and we can back off on the operating frequency in order to avoid excessive power dissipation. And just as a reference, I'm showing you that while QCA needs to dissipate hundredths of a kT log 2 or thousandths of a kT log 2, modern transistors dissipate thousands of kT log 2 every clock cycle. So to investigate power dissipation, we're going to go back to the shift register. And this is a nice system to study because whenever bits are erased, erasures are done on the trailing edge of the bit packets, and every bit that's erased is done in the presence of a copy. So this, in theory, should be a very nice and adiabatic operation. So to investigate this, we're going to zoom in to the cellular scale and zoom in further to the molecular scale. And we're going to ask, what is this target molecule dissipating? And we're going to treat its two neighbors as drivers. And in this picture, I'm showing you a molecule that is presently under study for this very application. And to do calculations with this model, we had to go not to the two-state system, but to the three-state system. And it's very much like before. Here's the quantum mechanics, the quantum state for that three-state system. There's a 0 state, a 1 state, and now a null state. And the state is actually defined by a polarization and an activation. So activation is the probability of finding the cell on one of the active dots, and polarization is as before. Here's the Hamiltonian. It captures the energetics of this system, and we can use that Hamiltonian to calculate the cell-cell response. So here's a molecule, and a strong negative electric field activates the target molecule, and the target molecule goes to a state determined by the neighbors. Or a strong positive electric field, strong positive electric field will drive the system to the null state regardless of what the neighbors are doing. And I'm just showing that this data maps onto some experimental data for a metal dot QCA cell. So that Hamiltonian, we can take and construct a Hamiltonian for the coupled system, that is the electron with the vibron. And we can put that in the Lindblad equation. And I'm using this symbol D for the dissipator term. And I can use that to calculate the power dissipation from the vibron to the environment. So these two terms here are power from the environment to the vibron. So we take the negative of these to get power dissipation from the molecule to the environment. We can average it over a clock period to get average power dissipated. Or we can simply integrate it to get energy dissipated. And those results I show you here. So the clock goes strong negative, it activates the cells, and then it goes strong positive, nullifying the cells. You can see here the clock frequency is 90 gigahertz, which is pretty respectable. And with these molecular parameters, the system is dissipating 6.7 kT log 2 every clock cycle. Down at the bottom, you can see the vibron position on one axis, numbered -8 to 8, and then on the right you see the electronic position, and you can see that as the electron switches, the vibron deflects. In this calculation, I've changed the reorganization energy to 1 millielectron volt from 440 millielectron volts in the previous slide. So I've weakened the electron-vibron coupling, and now you can see that as the electron switches, the vibron hardly displaces, but yet we still get some good device switching, as you can see in the schematic picture of the molecules in 3D in the upper left. So a table here summarizes these results. Various values of lambda lead to different levels of energy dissipation every clock cycle. We can actually dissipate even less than 1/100th of a kT log 2 each clock cycle. And that enables us to just get below the limit of manageable power dissipation. And in conclusion, I point out that QCA really does have the potential to revolutionize computing, because molecular QCA can support terahertz scale switching speeds, and we expect manageable levels of power dissipation are possible at high operating speeds. So what we'd like to do is define or build models of QCA that allow for a theoretical design loop. So chemists can design a concept molecule, they can characterize it by experiment or calculation, and with their results we can take molecular parameters that they give us, and we can use that in our models to calculate electron transfer rates, quantum decoherence, and power dissipation. And that helps us get at device performance. How fast is the molecule? How much power does it dissipate? And we can suggest to the chemists that they could redesign the molecule, or we can even use our model to explore, hey, what are the optimal molecular parameters that are going to help us maximize performance. An additional question we can explore is, what clock design maximizes device performance? And future areas of interest focus on using the mathematics of QCA and open quantum systems to model research in other problems, such as the quantum mechanics of the sense of smell, or quantum computing and quantum communication theory. I acknowledge this support for the results I showed you previously, and I thank you for your interest and attention. Have a good day.